Welcome to AJ Khan Geotechnical Forum. Once again, I was talking about bearing capacity of shallow foundations. I have already covered part 1 and part 2 in my previous lectures, and today I am going to talk about part 3. So in part 3, we'll be actually talking about example problems. From problem 1 to 3, I'll be showing you about how to apply these equations for homogeneous subsoil, and also from 4 to 6, I'll be showing you about how to deal with multilayered subsoils. Okay, first of all, let us consider a special case for our following example. Case 1 here, and we are talking about phi equal to 0 condition and vertical loading, that is alpha will be equal to 0. Let me give you some idea about what is actually phi equal to 0 condition. This is applicable for clay soils, okay? It can be normally consolidated clay or it can be over consolidated clay, it doesn't matter. There may still be phi equal to 0 condition for both these types of clay soils. By phi equal to 0 condition, we actually mean that the soil is sheared in undrained loading condition. What does it mean? It actually means that the load is applied from the superstructure so fast that the water or the moisture from inside the subsoil, which is a clay soil of course, cannot rapidly expel out, or it cannot escape out from the soil system during the time of the loading. That means, for example, if you are constructing a steel structure, a factory building or whatever, which is going to be constructed in say 6-7 months time, because all the components, all the structural members are prefabricated, even if it does take about 1 year, that means the load is going to be applied very fast. So when the load is going to be applied very fast, the subsoil below the footing will hardly get enough time to get out from the soil system. That means the undrained condition will prevail in the soil. And that is what we call phi equal to 0 condition. Why phi equal to 0? Because the soil particles will not be able to come in contact with each other, and the friction between the soil particles will not be mobilized. That is obtained by triaxial test, and popularly the UU condition test. And from UU test, you will always end up with a phi equal to 0 envelope, and the cohesion value will always be denoted by C subscript U to emphasize or to highlight that the parameter is obtained from an undrained test condition, which is your practical case for this particular example. And for phi equal to 0 condition, the bearing capacity equations, which we have earlier populated in our part 2 lecture, that the NC will be this, NQ1 and N gamma will be 0. So the third term will not be there anymore. Only these two terms will be there. And also you can calculate the shape factors and the bearing depth factors and the inclination factors using the equations we have shown in part 2 lecture. So your gross ultimate bearing capacity equation for this particular condition will be this. Okay, this is the expression, and you don't have to use any chart for determining this gross ultimate bearing capacity. And the net ultimate bearing capacity, we have talked about the gross pressure and net pressure in our part 1 lecture, and that actually means the gross pressure minus the effective overburden pressure, which is Q, we know. So the net ultimate bearing capacity will be gross ultimate bearing capacity minus the effective overburden pressure at the excavation level. So this will give you QU minus Q. That means only this expression will remain there as your net ultimate bearing capacity. And always remember, we'll always finally calculate the net ultimate bearing capacity, and on the basis of this net ultimate bearing capacity, you will be calculating the net allowable bearing capacity. This is net allowable bearing capacity, which is given by QNU divided by factor of safety. And the additional load that will come in excess of the effective overburden pressure, that always has to be compared with this Q allowable, which you will obtain on the basis of the net ultimate bearing capacity, not on the basis of the gross ultimate bearing capacity. Okay, so this is actually significant for us, but for calculating this, you'll always have to calculate this. So let us take an example of this particular situation. Say below this footing, which has a dimension which has dimensions of 3 meter by 3.5 meter, and the water table is somewhere there at the ground level, and the soil below this is of course up to the depth of excavation is saturated unit weight, and this is 16 kilonewton per meter cube. The depth of foundation is 2 meter, and the soil properties below this footing is this. So this is like undrained situation. We are analyzing for an undrained situation. That means the load will be applied very rapidly within a very short period of time, or in other words, the construction period is very short. And the unit weight, obviously this has to be saturated unit weight because the water table is up there, and the saturated unit weight is 18 kilonewton per cubic meter. And all these soil properties in this example, we have assumed that this is this soil actually extends up to an infinite depth, and this is a homogeneous soil. Okay, so picking up the right equation here, just as I showed in my last slide, this is your equation for the net ultimate bearing capacity, and just by putting the values here, you will get this net ultimate bearing capacity value, and then the allowable net allowable bearing capacity on the basis of net ultimate bearing capacity divided by factor of safety equal to 3. In some course it is 2.5, and that will give you an allowable bearing capacity of 170 kilonewton per meter square. That means you can't apply any net load which will cause a net pressure more than this. This is not allowed. Okay, so this is the safe bearing capacity, safe allowable bearing capacity of this subsoil for this footing size and depth and the hydrological properties. Okay, that means the net applied load, the net load that you can apply safely is equal to Q allowable times the area of the footing, and that will give you 1791 kilonewton. So that means you can, on this foundation, with these given parameters and subsoil conditions, you can safely apply a net load. See, this is calculated on the basis of net ultimate bearing capacity. So everything here we are talking now is net, okay, not gross. So this is the net load that you can safely apply to this footing. Okay. Now let us move on to another case and example. Of course, here C is 0 and the loading is absolutely vertical. That means alpha is equal to 0. When you have alpha equal to 0, you have all the inclination factors, this one, and this one, all these are 1. And now let us talk about what are the situations where you will always have C equal to 0. You may have phi but no C. Let us talk about that. Okay, first of all, if you have sand, absolutely in sand there is no question of C. Okay, just forget about it. In sand you always have angle of internal friction phi. Fine, fantastic. But often we have a misconception that in clay soil you can't have phi. No, that is not true. In fact, in some clay soils you may not even have C. That is very interesting. For example, for normally consolidated clay, you will never obtain C value from any test unless it is a UU test. From UU test, yes, you can get. From UU test for NC and from OC, you will get C. But for normally consolidated clay, if you are conducting a CU test or CD test, you will not obtain C value, you will only get phi value as shown in this figure, and all these figures are available in all the textbooks. You can pick up any book, B.M. Dash, Tomlinson, Bowles, or whatever, you will find all these things, and all the concepts are very much clearly written there. Okay, so keep it in mind. It doesn't mean that for a clay soil, for any test condition or drainage condition, you'll always get C. No, that is not correct. That is not true. For example, in this case, for normally consolidated clay, if you are conducting a CU test in triaxial or a CD test, then you will end up with only phi value, not C value. For CU test, that is in undrained condition, you will get phi which is lower than the phi prime which you will obtain from the CD or the drainage condition. When the drainage is allowed, that means the load is applied very slowly. If you are constructing a 100-story building, for example, and very slowly, that means the moisture inside the soil, from inside the soil system, will get an ample of time to expel out from the system. That means the soil particles will come in contact with each other, and more internal friction will be mobilized. That is why under drained condition, you will always have more angle of friction than in undrained condition for NC clay soils. So your first part is gone because there is C here, and for this condition there will be no C. So this part is gone. You will only have second term and the third term of the equation, and that is equal to this. And the net ultimate bearing capacity is obviously this one, and that will finally you will get Q equal to NQ minus 1. That means Q NQ minus Q. Actually, it is all the same. And this is your expression for calculating net ultimate bearing capacity for such cases. Okay, and from there you can obviously calculate allowable bearing capacity for this foundation. And please remember all the factors, the bearing capacity factors, inclination factors, inclination factors is one, the depth factor and the shape factors, all these should be calculated based on phi or phi prime, depending on what situation you are dealing with. If you are dealing with CU condition, you should be use phi. If you are dealing with CD condition, then you should be use phi prime. So this is the example here. We have considered a normally consolidated clay below the footing, which and also the drained condition. That means the load here will be applied in a prolonged time. Okay, so it will come very slowly. It is not it is not a situation like constructing a steel structure within 6 or 9 months. It is like constructing something in 4 or 5 or 10 years. Okay, so that means the loads will come gradually, and you have ample of time for the soil system will have ample of time to expel the moisture from inside the system. So the drain condition, C prime is equal to 0, phi prime is 35 degree, and all the other parameters are same as before. And just by picking up the right equation here and calculating it correctly, as I have shown here, you will end up with a net safe allowable load that may be applied to this foundation is 5032 kilonewton, which is quite high, of course, and it has to be high. When you have phi, you always have more bearing capacity and more load that you can allow on the foundation system. Let us pick up the third case, that is the case 3, where you may have C and phi both. Okay, and this situation may exist for over consolidated clay. Either you obtain the parameters for CU condition or for CD condition. See, please always try to understand that there is nothing like for clay soil you always have C and no phi, and there is nothing like you may have C and phi both. It is not like that. It always depends on the rate of loading you are applying. It is very much connected to the construction sequence and the speed of construction that is practically going to happen. Okay, so you just can't pick up any value or any parameter and use it. Sometimes many engineers come and complain that you have conducted a CU or CD test for a normally consolidated clay, but you have not given any C value. It is not. In fact, a normally consolidated clay should not have any C value for CU or CD conditions. So the test result was correct, but the engineer, he or she actually misinterpreted the test result, forgetting the basic of soil mechanics. So for over consolidated clay, for CU and CD condition, you may have CU or phi U, as I have shown here, or you may find it in any textbook. And for drain condition, of course, you will have C prime and phi prime. Please remember, this is valid up to the pre-consolidation pressure of the soil. But beyond pre-consolidation pressure, this soil will become a normally consolidated clay. So in that case, you only end up with having angle of friction and no C value. So it is also very important, although you are dealing with an over consolidated clay, you must have to know that what is the working stress that is going to come onto this subsoil. If it is less than sigma C prime, that is the pre-consolidation pressure, you are very much right, you can use both C and phi. But if the working applied stress exceeds this pre-consolidation pressure, then you can't pick up C and phi. You should be using only phi values in your calculation of bearing capacity equation. That means this will become a case 2. Okay. So by having understood all these things and having said all these things, here only the FCI, FQI, and F gamma I will become 1, and all three terms will remain there, of course, and the net ultimate bearing capacity is of course this minus this, and the allowable bearing capacity you can calculate by dividing the net ultimate bearing capacity by a factor of safety. So this is the example here. The soil here is over consolidated clay and the C value is 25. We are considering an undrained condition, and phi is 15. The other parameters are all the same. Just pick up the right equation and calculate all the factors, the bearing capacity factors, shape factors, and depth factors, all these things, and substitute correctly, and you will end up with the net allowable load that may be applied to this footing or the foundation. Okay, very simple. Okay, so far what we have discussed is we have considered a subsoil condition which is homogeneous up to an infinite depth below the footing. But such situation is more of academic purpose. You know, it hardly occurs in the real life, does it? It doesn't. But more frequently, you encounter multi-layered system, okay, multiple layers of subsoil. For example, in this example number 4, what I have considered is you may have a situation where you have first 1 meter of clay soil, then next 1.2 meter is again of clay soil, and the next layer, that is 2 meter depth, is also clay soil. You may have all clay soils, okay, and up to an influence zone or zone of influence, which is equal to B of the footing. So H, the zone of influence is H is equal to B, that is 3 meter in this particular example. Okay, that means your zone of influence will penetrate in the third layer, and in the third layer it will penetrate only by 0.8 meter. 1 plus 1.2 is 2.2 plus 0.8 is 3 meters. So this is your zone of influence. So what you do now is for addressing or for calculating bearing capacity of such multiple layers of clay subsoil for this footing, you'll have to calculate an weighted average of the cohesion values, because the phi equal to 0 condition has been considered here. So you'll have only the cohesion values here. So 25, 30, and 20. So how to calculate it? 25 times 1, that is the thickness. 30 times 1.2, that is the thickness of the second layer. And 20 times 0.8, that is the thickness up to which, or the depth up to which, the zone of influence penetrates into the third layer. And divide it, the whole thing, divide by 3. So that will give you the weighted average cohesion value of the soil system within the zone of influence, and this is 25.67. So this is kind of, you have modified the soil system to a fictitious soil which has a cohesion value equal to 25.67. Okay, and then you have nothing else to do. You'll just need to follow the steps in example 1, which was a case for which was case 1, and that was for phi equal to 0 condition, and that was for clay subsoil. Okay, fair enough. And next example, here we have, say, multiple layers of sand. Okay, similar. So the zone of influence is like this, again equal to 3 meter, and penetrates 0.8 meter into the third layer, and the weighted average angle of friction is tan inverse of 1 meter times 1020 plus 1.2 meter times 1030 plus 0.8 times 1018 degree whole divided by 3, and inverse tan inverse of that will give you an angle of friction equal to 23.7 degree. That means you have modified this whole subsoil up to the zone of influence into a new subsoil which has an angle of friction equal to 23.7 degree. So your problem now becomes same or similar to the problem shown in example 2. So follow just those steps as shown in example 2. Right? Now let us come to a rather more, because in example 4 and 5, in example 4 we have considered multiple layers of clay subsoil, and in this example, in example 5, we have considered the multiple layers of sandy subsoil. What about if you have clay and sand layers, kind of mixed, okay, everything together? So let us say in the first one you have sand, okay, which has angle of friction equal to 20. In the second one you have over consolidated clay, so you have C and 5 both. In the third one you have you have clay soil, which is fine, 70. And in the fourth one again you have over consolidated clay, which has cohesion value of 60 and angle of friction of 15 degree. It is not 150, it should be 15 degree. Okay, now what to do? Similar approach. In this case you will have to calculate both weighted average of cohesion and weighted average of angle of friction, as I have shown independently in example 4 and 5. So how to do it? In the first one, cohesion is 0 times 1 plus 50 times 0.7 plus 70 times 0.5 plus 60 times 0.8, and divide the whole one by 3, okay, because your zone of influence is 3. So here although it was 0, we have considered it just for clarity purpose, okay, just to show that you have to consider everything and take weighted average of whatever value of cohesion you have within the zone of influence. So this gives you a fictitious soil which has a cohesion value equal to 39 kilonewton per meter square. It is not 50, it is not 70, it is not 60. Now you have a new soil which has a cohesion value of 39. And similarly, the average angle of friction, tan inverse of 1 times 1020, then 0.7 times 1016 plus 0.5 times 10 plus 0.8 times 1015, divide the whole one by 3 and then take tan inverse, and that gives you a fictitious new soil which has an angle of friction of 14.6. So having said that, or having obtained these two values of cohesion and angle of friction, you just have to follow the steps shown in example 3. Okay. So thanks very much. I think you all have understood the lectures very clearly. Always remember, for calculating bearing capacity of foundations, you'll have to have a very clear concept of gross pressure and net pressure, then gross ultimate bearing capacity and net ultimate bearing capacity. And actually finally what we compare is net allowable bearing capacity with the net applied load, okay, or net pressure. So that is what we are talking about. So finally we come down to net. It is not gross. We dimension the footing on the basis of net pressure and net ultimate bearing capacity. We allow the load on a given size of footing on the basis of net allowable bearing capacity of the foundation. Thanks very much. Thanks for watching all these 3 lectures. Be with me and always be connected to AJ Khan Geotechnical Forum. Thank you all.